Today we're going to talk about HPC hardware and kind of how what is available on the systems and how you can find out more information about it and how you can monitor your system. So if this is your first time joining us for Complex, Complex is a special training program specifically designed for the non-programmers. Way I kind of like to think about it is that there's those of us who use HPC systems as a tool, and those of us who use HPC systems as a playground or a toy. And if you're not really programming, this is more of a tool for you. So this is more the tool people, but maybe after this presentation, more of you will feel that it's more something you want to play with. So today, I have the presentation split up into kind of three different parts. So we're going to start and just talk, kind of refresh your memory about what an HPC system is. And then sprinkled throughout the presentation, when I bring up different hardware topics or software or tools, we'll talk about why those different why the different hardware is important to you as an end user. So I'm going to start on kind of the high level and we'll talk about what exactly is on the system or how you can find out what exactly is on your systems. So operating system and kernel are not hardware, but it is important to know about those to find out more information about the rest of your system. So we'll do the high level, theoretical, and what's actually on the system. Then we'll go a little deeper and look at how the system is actually being used, kind of on a grand scale. And then we'll very briefly touch on how your particular jobs are touching on the system. It's more a schedule. There's some scheduling tools, so we have a whole presentation on scheduling. But we'll look at that just briefly at the end there. So this first slide I actually borrowed from Marty. And I'm going to use this to kind of recap what HPC systems are. So a high-performance computing cluster consists of multiple dedicated HPC processing nodes that are connected by a specialized high-speed network. And it's going to use some job scheduling software to facilitate the ability for you to process data and perform really complex actions at really high speeds. So for perspective, your laptop has 1 to 2 processors, and an HPC cluster can have hundreds of processors. And by using this network, you can put them all together so it looks like you're using an individual system. And the reason we want to use this is to improve the performance of whatever we're doing. So we want to solve problems more quickly. We want to scale to larger problems that we can't necessarily do on our laptop. And we want to do more small problems quickly. So increase your throughput as well. So in the previous slide, I mentioned that HPC facilitates the ability to do things quicker. It doesn't guarantee that you can do things quicker. So there's two very common myths. Users come to the system and they think just because they're on a supercomputer that their code is going to perform better. And that is definitely not true. They also think that if they throw a bunch of hardware at it, their code is magically going to be able to use all that hardware. So the big disclaimer here is that to be able to use the tools, your code needs to be specifically designed to be able to take advantage of those tools. A kind of side way of thinking about it is if you wanted to plant a tulip, you could very easily plant a tulip with a little hand shovel. You could also plant a tulip with a backhoe, but you would be throwing way too much. It would be very, very inefficient. On the other hand, if you wanted to plant 100 tulips, you could have 15 people, but you could only have 1 shovel. And even though you have the 15 people who theoretically could help you do this much quicker, if there's only 1 shovel, you still have to do it in serial. So you have to teach all the people and give each of them the tools so that they can do their work. So let's take a look at what actually the components of the system that we're going to talk about today. So again, HPC systems are a combination of hardware and software, and the hardware is going to be the nodes that are on there, and those nodes are going to be comprised of processors and accelerators, and those processors and accelerators are going to have memory associated with it, and there's going to be some storage devices associated with it. And there's going to be software and tools that enable you to use all those things. And all of this is going to be tied together with networking. So why do you care about again, if you're not diving deep into the weeds and doing the programming, why do you really care about the hardware you're running on? And there's three main reasons why you care. On kind of a high level, any jobs you run on a system, you're probably going to want to document how you ran those jobs. Depending on where you run it and when you run it, it may perform differently. So if you're doing proposals, if you're writing reports, if you're writing a paper, you're going to want to be able to reproduce your work. The second reason would be resource selection. So if you're on your laptop and you decide that you want to go to an HPC system, it's important to know if the application that you're using will be able to run on that system. The Access umbrella organization has a big portfolio of different resources that are available to you. So when you go there, you kind of want to know which system you should put it on and where you will get the best bang for your buck. The other reason is that HPC systems have a lifespan about 5 to 10 years, but during that lifespan, things can change. Other resources can come up that have better performance, or you can be on a resource that is just the queue wait times are too long. So you might want to move to a different system. So again, checking out the hardware that you're running on, you can see if you can actually port your codes over there and if you will get a benefit from doing that. The last reason why it's kind of important to know what you're doing is if you're running a code or if you want to port a code over and something's going wrong, you want to figure out why it's going wrong. So when you compile a code, you need to compile it for a specific architecture. You're going to also want to tune it for the specific architecture to make sure you get the best performance out of there. And you're going to want to make sure that you're using the most efficient resource. So there's three places we can obtain hardware information. The first one I'm going to mention, and I think that everyone who gets on a new system should always take a moment to use the user guide. I was on a call yesterday where the system administrator was saying, yeah, no one looks at the user guide, but it really is important to go and look at the user guide. Not only will it give you a high level understanding of what the system is you're using, it's also going to give you policies that are specific to a certain resource. So policies include how many jobs you can run, how much memory you can use, how you're going to be charged for different things. So again, I could go on for this for days, but it's always important to check out that user guide. The other place is Linux tools on the system. So there's a lot of Linux tools out there. I should mention Linux tools because the system that I will be giving the examples from today is Expanse, and Expanse runs Linux. It should be noted that for HPC, a Linux operating system or kernel is not unique. All of the HPC systems in the Access portfolio also use Linux, and all the systems on the HPC Top 500 list use Linux. So if you have a system that runs Linux, if you have access to Expanse or any of the other HPC systems in Access, feel free to log in and play around with this. Like I said, my examples will be on Expanse. But so we will be specifically looking at the Linux tools for collecting the architecture information. And a lot of the Linux tools pull their information from the pseudo-file system. And we'll talk more about that in a couple slides. So the first thing we're going to talk about is not hardware, but it's the operating system and your kernel. So it's important to know what kernel or operating system you're using, because it's going to kind of tell you what language you're going to be speaking with your system. And so why is the kernel important? So basically the kernel is system software, which is part of the operating system. Your operating system provides you an interface between you as the user and the hardware, and the kernel is providing you the interface between the application and the hardware. So the first thing we want to know is what kernel we're running on. So if you just type the uname command, it will spit back the kernel. In this case, you would just get Linux. But if we want a little bit more information, we can use the -A directive. And so it will tell us the kernel. It'll tell us what node we're on. So login2 is actually the login node on Expanse. It'll give us the version that we're running, and it will tell us when that version was built. We can get some additional information about the Linux distribution by going into etc CentOS release. We can see that we're running Rocky Linux 8.9. So the first thing we're going to look at is our nodes, and to find out the processor specifications. So the command we're going to use here is lscpu, and the lscpu is going to provide all sorts of information for you. Kind of the top things that we'll focus on is the number of processors, the processor type or model, the clock speed, number of cores, the cache sizes, some more information about memory. So when we use the lscpu command, this one was run on Expanse compute node. There's a bit of really important information for every user. The first thing that's really important is the CPU's number. So on Expanse, it's 128, and those are logical cores. And that number is derived from knowing the threads per core, which on Expanse is 1, the cores per socket, which is 64, and the number of sockets, which is 2. Other information that we can gain from, this command is more information about our cache. We can see the size here and the levels that we have. We also find from here is about how many NUMA nodes we have. So this is a SMD system, and it takes advantage of NUMA nodes. We can see that there's 8 NUMA nodes, and so we can kind of see how the memory is split out between the systems. Last important bit of information that we get here is the flags, and the flags are kind of the features of your system. So if you want to think about it as like a car, it would be your heated seat, or your heated, I don't know, your 20 cup holders. Again, just because the flags are available doesn't mean necessarily that your application can take advantage of it. I bought a minivan that had 20 cup holders, but only 8 seats. So granted, there were 20 of them, but no one was ever going to use them. So it didn't necessarily make sense for me to have them. There's a link here on the bottom that gives you that if you click on it, it'll explain exactly what all these flags mean. So what we didn't learn from the previous slide is kind of the cache to CPU association, or how the different cache types are associated with each CPU. So we can get that information if we use the -E directive with the lscpu command. And so what we see in that first column is the index number for each of the logical cores. So remember, we had 2 sockets. Each socket had 64 processors, so we had 128. So the index starts at 0, so we will have 0 to 127 CPUs. Our node is the NUMA node that we discussed earlier. So there are 8 NUMA nodes, which means that 8 divided by 128. So each NUMA node will be associated with 16 CPUs. The core, as I mentioned, there are no threads on Expanse. So that means that each logical core is associated with 1 physical core. And then we can also see how with our cache, the L1D, so the level 1 data cache, the level 1 instruction cache, L2 cache, and the L3 cache. Did I skip something here? Oh, I feel like I did skip. No, I didn't. Sorry, I got lost there for a second. So we can see over here a little bit of how the cache is separated out. So your cache, you get better performance the closer it is to your CPU. So L1 and L2 and cache are both associated directly with a logical core. The L3 cache is shared with 4 cores. So we mentioned, I mentioned in the previous slide that threads per core is equal to 1. And so I'll talk a little bit more about what this means. So SMT is the ability for a CPU to split its physical cores into virtual cores or threads. And this allows you to, theoretically, it allows you to increase the performance by allowing multiple instruction streams to run in parallel. You have to be a little bit careful with this because this means that you're sharing resources with the cores. So while you can improve your performance, you can also take a hit with performance on these things. At the tail end, we were talking about the flags. And so there were 2 flags that I kind of wanted to talk about that were mentioned for expanse, and that's AVX and AVX2. So AVX stands for Advanced Vector Extensions, and they're SIMD extensions that are specifically for AMD and Intel processors. And so these the instruction sets that theoretically, again, allow you to perform to improve your performance. So when you use it without AVX, you can, when you go from nothing to with AVX, you can theoretically run improve your performance by 4 cores per cycle. If you use AVX2, you can improve this by going up to 16 flops per cycle. So Expanse does not have AVX 512, but this is an option out there that is available on different systems. But again, just because it's there doesn't mean that your application can take advantage of it. It's very difficult to program to make this efficient. In addition, when you're using these different features, it could slow down the clock speed because it's doing a lot more work. However, if you do have a code that can take advantage of AVX 512, you can go onto the Access portfolio and see which systems have it. Specifically, Skylake does have AVX 512. Again, just because it's there doesn't mean your code can handle it. So I mentioned before that, so the lscpu command pulls its information from a pseudo-file. And so I want to talk a little bit about what exactly a pseudo-file is. So a pseudo-file is really a file, or a pseudo-file system is really a file system that doesn't have any actual files in it. And rather, it has kind of virtual entities that dynamically create themselves. So if anyone's a Harry Potter fan out there, this is kind of like the room of requirements for finding system information. So what the pseudo-file does is it contains information about what's currently running on your system. This isn't going to persist across multiple reboots, and it only exists kind of in RAM. So there's two systems that we're going to pull a lot of our information from, the /proc and /sys. So the lscpu command, much of the information we pulled from there came from this pseudo file proc CPU info. The difference is lscpu provided you nice summarized data about all the processors on that system. The CPU info file, pseudo file, will actually give you information about each core on there. So you can get a lot more information, and it's listed per core. So for instance, if you were interested in to see how each individual core, what the clock speeds were for it, we can check for that. in addition to that, it will give you, this is kernel information. It will give you information about any bugs that it detected or addressed, and also give you some other low-level information like microcode, table sizes, and stuff like that. Oops. Sorry, my computer is stalling here. There we go. Well, so one other thing to note is that these pseudo files can have a lot of information. If you just run a cat on this file, it'll give you out about 2,000 lines of code. So you can go through it and you can dig through it and find out very interesting information, or you can use some scripting tools to pull out specifically what you want. So for example, if we're just interested in the speed, we can use CPU megahertz grep for that, and it will pull that out. Other things that I put in that scripting is head 5. It is just giving me the top 5, reporting just the top 5 from that. The second section down here is just the information I mentioned, is additional information that you cannot get from the lscpu command. So another thing that we kind of need to consider on the HPC systems is that they're not homogeneous systems. There are login nodes, there's compute nodes, and there's data mover nodes. And all 3 of those nodes they're specifically designed to do certain tasks. So for instance, the login nodes, we don't want people running codes on them. So we actually limit what we allow to be done on there. So the login nodes, yes?
I'm sorry, can I interrupt 1 second? We had a request, and I don't know if this is something you do on the fly, to change your pointer so that it's more, I think, so that it's more visible.
I don't think I'm using the pointer. If I am, it's inadvertent.
Okay.
I'm
All
sorry.
right.
But I apologize. I don't know how to change it. I've never done that before. I will stop moving the mouse around. I'm sorry. Nervous habit.
Great, thank you.
Okay, so different types of nodes. Login nodes are specific for simple tasks. We don't want people running out of memory there. We don't want people doing CPU intensive tasks there. Then we also have the compute nodes, and the compute nodes, in addition, are not always the same nodes. So on Expanse, we have 3 different types of nodes. We have regular memory nodes, we have large memory nodes, and then we have GPU nodes. So when you're compiling codes, it's so you need to understand the architecture on the node in which you need to run, not necessarily just the login node. Again, if you're compiling codes on Expanse, you would need to actually get an interactive session for GPU, say. You would need to get an interactive session for GPU, log into the node, and compile on the type of nodes that you're going to run eventually. The other type of node is we have the data mover nodes. So the data mover nodes actually do have multi-threading allowed on it. We have the data mover nodes there very specifically so that people can go there to move large amounts of data. Therefore, the threading is useful and it's not going to affect other users. With that in mind, let's take a look at the specifications for the GPU nodes. So we can see here that the CPU's logical cores are 40. Again, this is single-threaded. Threads per core is equal to 1. Cores per socket is 20. Sockets is 2. The NUMA nodes here is now 2, which is different. We can also see that the cache are different sizes. L1 and L2 are still 32K, but L2 and L3 are a little bit larger. Then we can see how the NUMA nodes are distributed between the two. The cores are distributed between the 2 NUMA nodes, and then the flags that are available with this type of node. If we use -E, we can see that the CPU indexes are going to run from 0 to 39 for the 40 CPUs. There's also, since there's 2 NUMA nodes, the CPUs alternate between the 2, same as the 2 sockets. Again, since there's a single thread per core, each physical core is going to be associated with a logical core, along with the L1 and the L2. But for L3, since there's just two NUMA nodes, the L3 is going to be shared with 20 CPUs between those two. So I don't know if you noticed, but when we did LSCPU on the CPU and the GPU node, it didn't mention anything about GPUs. So we'll look at a couple tools how we can find out if a GPU exists and what is on there. But let's step back for a second and just refresh everyone's memory on the differences between CPUs and GPUs. So the CPU is kind of the head chef in the kitchen. The CPU handles all the tasks that are required for all the software on the server and to make sure that everything's run correctly. The GPU, on the other hand, is there to support the CPU, and it performs really specific concurrent calculations. So what the GPU is designed for is to complete really simple repetitive tasks really, really quickly. And it does this by breaking down the tasks into small bits. So while you can have a GPU node, well, while every GPU node will have CPUs associated with it, all CPU nodes do not need to have GPUs associated with it. So how do we know if there's a GPU there? So on Expanse, we can use the NVIDIA SMI command. If you run this on the login node, it's going to tell you that it can't find the driver. If you run it on a system that has no notion of the driver, it will say command not found. So to actually see this information, you have to be on a node that has a GPU. So to get this information, we had to interactively log into a GPU node. And so what we see here is highlighted in red, that 0 is the index of the GPU. Our nodes have 4 GPUs. It tells us what type of GPU we have. So we have Tesla V100s. It can give us the power consumption, so it's usage over capacity. So the total capacity is 300 watts, but we're currently only using 67 watts out of it. We can also see the memory usage. There's 32,510 megabytes, and we're currently not using any of it. And we're also currently, the GPU utility shows us how much we're using of that. It says 0%. And if we look down below, we can see that there's no running processors found. So it makes sense that it's 0%. There's two other places that we can find if a GPU exists. So the LSPCI is a command for displaying information about the PCI buses on the system and the devices that are connected to them. So since a GPU is a connected device, you can search the output and extract the needed information. So this command also has a very large amount of data that comes out of it, a little less than for the other command. This only has 300 lines, but still more than you want to look through. So again, using our scripting tools, we can specifically look for the 3D controllers. So if you grep E for VGA or 3D, it will show you that you have the controller, and then it will show us our four devices. The other command that we can use is LSHW, which stands for list hardware. This is another one of those files that has a ton of output. So we're going to want to specifically look for these display devices. I'm showing you just the top of it. When you run numeric-c display, it'll show you what we saw before. We saw the controller, the compatible controller, and then the 4 devices. So the top is just the controller, and then down below we see the first listing for our Tesla V100 node. Another another aspect that is important to us for the performance of our system is the cache. The closer the cache is to the CPU, the quicker or the better the performance. We saw this information with the LSCPU, and now we're going to look at the pseudo-file that can give us, or the pseudo-files that can provide us with this information. So I mentioned that pseudo-files, you get information specifically for all the individual cores. So if we actually drill down into this, so we're in sys devices, system CPU, you can see that they're, and I don't list them all, but it will list all the CPUs. So it will be CPU 0 up to CPU 127. Once we know which, we can look into the individual CPUs and see what is on them. So if you go into CPU 0 and we can go into the cache directory, it'll show us that we have 4 indexes, which is a little obscure. There's 0, 1, 2, 3, but to find out exactly what those are, we can drill down a little further. So if we're just going to take index 0 first. When we go into index 0, you can see all the information that we can find out about that cache. So specifically, you can go in and you can see, again, what the ID is at 0. We can see what level cache this is. This is level cache 1. We can see the size of it, which is 32. I'm using my thing again. I apologize. And we can see the type of data. So if this were our L1 instruction cache, that type would be instruction. So another useful pseudo file is the meminfo file. So this is going to give us a usage report about the memory on the system. The most useful lines are going to be probably the top 2, or no, the first one and the third one. So the total memory is kind of our total physical memory that's available on the system. The memory available is what is actually going to be available to resources for non-system stuff. We have the 3 different nodes on Expanse. We have the regular memory, the large memory, and the GPU memory. And so just to kind of show the difference, I pulled up the 3 different ones. I had the listing of the meminfo for all 3 of them. So our regular memory nodes has 256 gigs, our large memory has 2 terabytes, and our GPU nodes have 384 gigs. One of the reason why this is important is, and again, this comes down to policies on the system, is does the node you're running on have enough memory for you? Very often we have users report to us that they're running out of memory, so they get an ohm kill, out of memory error. And in some cases, it could be that the node they're running on simply doesn't have enough memory. On the other case, it could be that users are not asking for enough memory in their submit script. So in our submit script, we require all users to request the amount of memory they're having. And so if you use less than is needed, it will tell you. So you can either increase the memory on the node itself, or you might need to move up to a different type of node, or move to a different system that has more memory available to it. So let's take a look at file systems and how to evaluate their usage. File systems are also pretty important. There's lots of different file systems available, and they're all kind of designed to handle different things. There's NSF, there's Ceph, there's Lustre. Some file systems handle some things better than other things. For instance, the Lustre file system doesn't handle lots and lots of really small I/O. So, sorry, something popped up in my screen. So checking out what file systems are available and what will be the most useful for your particular program is good to look at. Also, the different file systems, mentioning again that there's different policies regarding those file systems of what you can use and the performance that you can achieve on them. So we can pull file system information from the pseudo file system. We can also use some Linux commands to pull out information. We can also use file system specific commands to look specifically about specific usage on a certain file system. So there's the proc file systems and etc tab. So the proc file systems will list all the systems that are currently supported by your kernel. Just because they're supported by your kernel does not mean they're on your system, but it does show you what is there. The list on the right-hand side is not comprehensive. I have a couple dots in there, but it shows what that all the systems we have on there. And I actually tried to highlight the systems that we actually do have on Expanse. So Ceph is listed there, Lustre is listed there, NSF is listed there. If you want to know what file systems are actually mounted on your system, then you can use the etc mtab command. If you run this on Expanse, it is going to list everybody's home directory. So this is not very interesting for you. So if you're looking for a specific type of file system, you can again use the scripting language to pull out specifics. In this case, I pulled out just Lustre and Ceph. And so the previous command I ran on the login node. This command was run on the compute nodes. NVMe is not available on the login nodes. So, but if you, we can use the df command to provide us more information on the file system usage. And so I kind of have a list here of all the kind of the important file systems that are available to us. So the NVMe is the local scratch local to the node itself, and it's probably going to give you your best performance. Things to keep in mind though, this scratch, this space is only available while your job is running. So you have to move data on and off it. We also have community and SDSC maintained software stacks. And then we have our allocated Lustre space. So we have allocated project space in Lustre, and we also have scratch space, which is not allocated, it's just available to everyone. But if you take note that the size used, available, and percent used on both of these is the same. So in Lustre, the usage is evaluated by the group or the allocation, and not necessarily the directory that you're in. The other important thing is on this is that this, when you're on your node, you can check to see to make sure that your home directory is mounted. So the last bit of information that I think is useful when running codes is kind of identifying the SCSI devices. So this includes the NVMe that we were talking before. So if you can run this, if you run this on your login node, it's only going to show you the disk ATA. It's not going to show you the flash memory. If you run this on one of our compute nodes, you will see the flash memory available there. The du command is a Unix command for understanding how you are currently using your disk. So, but the user support team uses this quite a bit with regards to home directory usage. So lots of people get to a point and they say, I can't copy files anymore. What's going wrong? So with this, you can see how much usage you're using. So this comes back to the policies of the system. On Expanse, we have a quota of 100 gig. At other places, we have different quotas, but this is a quick way to find out if you're running up against any quotas. The du command has some 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 directives that are very interesting. So if you just run it normally, I think it gives you the output in kilobytes. To simplify it so that you don't have to count zeros, you can do the H command, which is human readable. You can use the summarize. So if you just run du, it will list all the files and their sizes. If you use the summarize, it's going to give you the total that is being used in that area. The one other interesting one is the -- time, and it's going to tell you the last modification of any file or directory. So this could be important if the resource that you're on has a policy of a purge policy that is based off of file last modification. I should put a disclaimer here. We have a purge policy on Expanse, but it's not due to last modification. It's associated with date of creation. So while you can run the du command on Lustre file systems, it can bog it down. So it's better to use the LFS command, which is Lustre specific. Again, I mentioned that Lustre is evaluated based on the group that the file is associated on, not necessarily the directory it's in. So you can use the command lsf quota-g, your project ID, and then the path, the Lustre file path that you're looking to evaluate. So one of the things that makes HPC is the networking. The connectivity between the compute hardware and the storage allows you to scale up nicely. The interconnects are designed to provide interprocessor communication. Apologize. Along with various individual servers. So it allows all the compute nodes to behave as like one large single system. So while processor speed, the amount of nodes that you're running on is really important, the other important thing is to consider the performance of your interconnect. So on Expanse, we have three. There's Ethernet, 10 gigabit Ethernet, and a InfiniBand. So as the first implies, Ethernet, it has transmission speeds of 1 gigabit per second. It's a switch network, which is nice because it allows switches to be daisy chained together so that you can add additional ports. We also have a 10 gigabit Ethernet connect, which, as the name kind of implies, is 10 gigabits per second. So it's 10 times faster than the regular gigabit. We also have InfiniBand, which is even faster than 10 gigabit, and it has lower latency and is obviously faster, with average speeds about 40 to 56 gigabytes per second. So while the network is kind of something you just have to deal with, it is good to know what you have so that you can manage expectations, I guess. So we can find out what networks are available with the IP command. If we use the IP command, look for link, we see that it has a list of everything that is there. The prefixes, the EN stands for Ethernet, the IB stands for InfiniBand. We can see that we have both Ethernet and InfiniBand on Expanse. So now I'm going to transition a little bit. We started by looking just what the system has and kind of on a high level what's being used. Now we're going to look more specifically on how exactly the system is being used at this moment in time. So we can monitor the resource utilization per node with a couple commands. We can use the PS command. There's a series of top commands that we can use. There's an MP-stat to provide us some processor statistics. We can use the SAR command, which gives us a system activity report. We can also use the free to learn more about what memory is available to us at any given time. And then we'll look again at NVIDIA and what we have. Or I'm going to mention again, because I think I talked about already the information that comes with the NVIDIA SMI command. And then I'll mention two Slurm commands that can that will help you evaluate specifically how your code is taking advantage of the system or how it's using the system. So the PS command or process status lists all the running and current processes on your system. This can be this can be a lot of information. If you ran this on the login node, you'll see every single person who's currently logged in the system. We have 2 login nodes, so they are split between 2, but it will give you this information. Very often, the user support team will use this command to figure out what's going on in the system. And if we're running into problems, it will let us know what people are doing on the system, how many people, so we can see if people are doing large data transfers, if they're trying to run programs, so that we can contact users and maybe throttle what they're doing on there. The other reason we sometimes use this is when people have problems, for instance, with our Expanse portal, when they can no longer log in, it might be that they have some stale processes running, and so we can go in and kill those processes and clean stuff up. So there's a family of commands, the top commands. There's top, htop, and atop. And they dynamically display Linux processes. It's kind of a real-time view of what's running on the system. The top command is by default loaded or on all Linux systems. The htop and atop are kind of the top on steroids and give you other features, but they have to be separately logged, added into the system. So I'm going to spend a lot of time talking about the top command, because a lot of the information that we get in the top command we can find in the other 2 commands, but and then I'll just highlight the differences between htop and atop. So as mentioned, top utility is found on all Linux systems and provides a high level of running processes. It should be noted that this doesn't provide anything on profiling. However, there are some things you can do to kind of check your system. For instance, if you can watch the memory and how much memory it's using, and if it's growing over time, you might have a memory leak. But some of the things that we can use this top command is kind of see how many of your processes are running, how many processes are running in total on the system, what are the states of those processes, which cores those processes are running on. You can see if there's any competing processes. We can also see which processes are using the most CPU or the most memory intensive. So the top, all 3 of these top commands are really nice because you can tailor it to what you're specifically looking for. So by default, the top reports just on the processes. It doesn't report on any threads. If you did want to see threads, you can toggle with the capital H while it's running. By default, the top command shows you information for all users. If when you launch it, you have a specific user that you want to look at, you can do top-u and the username. But while it's running, you can also hit the lowercase u and specify the user who you're interested in looking at. You can also limit it to just the number of processes. By default, as I mentioned, if you're looking at memory or CPU, it will use the top, the ones using the most CPU or the most memory at the top. So if you're only interested in who's using the most at the top, you can limit it with the -n and say, I just want to look at the top 5 or top 10. By default, I said this was interactive. It updates every 3 seconds. You can change that if you want that a little slower, a little quicker. When you run it, it is ordered by CPU usage. If memory is more interesting to you, you can change that by capital M. I'll show you in the next slide all the information that it provides, but some of the listing is there. You can put processor ID, the priority, the nice level, virtual memory, all that good stuff. If you can change that with the F command, so you can change the fields or limit the commands. One other really cool feature is the C command, which displays the full path to the process or the command line. So we, as user support, when we run this command, if we see someone who's doing something that might be questionable, we can actually check out what they're doing by looking at the file, because we know where it is. So this is an example of the output. The top section, excuse me. So the top section of the window shows kind of system information, and then the lower section is the running processes themselves. This also, so it gives you information about CPU, it gives you about the memory that's being used and the swap space that's available. So the htop, did I skip? No. The htop command is not built in like top, so it needs to be installed on the server. And the output to the htop utility has the same structure. On the top, there's information about the system, the CPU load, the RAM that's being used. It shows the average load for 1, 5, and 15 minutes. And then below that, it has a list of all the processes sorted by CPU by default. So again, this is interactive and it's colorful, so you can see a little bit more here. If you want to change what you're seeing or all the options, you can use F1 for help. And you can see in the bottom right there, those are all the different parameters that you can throw at this to change how you see it. Kind of the most important ones are you can sort by memory, you can sort by processor, you can sort by time, how long something's been running, or the -U for a specific user. The atop command is same thing. It displays load for the system's resources at the process level. It's useful for diagnosing floating errors. It allows you to keep logs and monitor work of processes over a period of time. This too is not built in. It has to be installed on the server. So what's additional features is you can look at this for actually using disk usage, and the AU is processes per user. So the MP-stat will allow you to report processor-related statistics. It accurately displays the statistics of the CPU usage of a system and the information about CPU utilization and performance. So when you use the MP-stat command, it's going to display in 2 sections. The first section is going to display the system configuration, and the second section is going to display the utilization statistics and in intervals. Excuse me. And they're displayed, the values of these metrics are in the deltas from the previous one. So you can see, so the first thing you see is that for all, you kind of have summary of everything. And then after that, at 8/19/33, you're going to list for every single core and the statistics it is, and this will go over time. Again, this is just a very brief section of the top, an excerpt of just the very top of what we're seeing. So the SAR command, SAR stands for System Activity Report, reports on the various system loads that include CPU, memory, network utilization. The SAR command writes to standard output and the contents of selective cumulative activity counters on the operating system. So when we use the SAR command to monitor the Linux system resources like CPU, memory, or the IO devices, excuse me. This also shows the delta between time. So the next thing we want to look at is the free command, and this is to evaluate the memory usage statistics. So the free command displays the total amount of free and used memory on a system, including the physical and swap space. It also gives you information on the buffers and the caches that are used by the kernel. So this information is also is pulled from the pseudo-file mem info. And the main column of interest is the available column. And this column is kind of estimating how much memory is available for starting new applications without swapping. We've already kind of looked at this, but I wanted to bring it back in here because this is actually where we can, this is where we're getting our GPU information about what's currently being run on the system. So again, this is identical to the one we looked at before. If there were processes running, we would see down here, the GPU would be the node that it's on. So it get 1, 2, 3, and the process name that is running on it and the memory usage. So now let's look at the jobs on a specific system. So this is going to be a little quick. These are both associated with the Slurm scheduler, and these both allow you to look at how your particular job is using the system. So the two is the CEF command. The CEF stands for Job Efficiency Report, and this command needs to run on the system after, or you need to run it on the job after the job is completed. If you run it before the job is completed, you'll get information, but the memory information that will be garbage. The output you'll get will be, well, I'll show that in the next slide. So S-ACIT actually stands for S-accounting. And S-accounting, this is a really powerful command. It has a lot of information for you, and you can use the directives to limit exactly what you're finding there. This you can run at any time. You can watch it while you can find information about your job while it's pending, running, and when it's finished. Unfortunately, neither of these give any information about GPU usage, just CPU and memory. So the CEF command tells you the job ID that you're running on, the cluster that you ran on. It'll tell you what user and group ran, the state when it exited. It will tell you the resources you requested and how you used them. So we have memory and CPU utilization here. Unfortunately, this job failed. So for the S-ACIT command, it's the same job name. So we can see that, again, we see a little bit less information because we don't have the user, but we do know the account was run against. We know how many resources it requested and that it failed. If you use the S-ACIT command, you can, as I mentioned, it is a very long, broad list of information you can get, and you can find all sorts of things of what was requested, when it started, when it ended, et cetera, et cetera. So I'm just about out of time. So in conclusion, I hope that I provided some information about the hardware components that are on our HPC systems, and how you can find out more information about them, why it's important for you to know about them. And then I gave you, I hope I provided some tools that'll allow you to kind of evaluate your system in the future, monitor your HPC resources and your jobs. The next two slides are just cheat sheet of all the files or the commands that we kind of discussed in this talk. And then I just have a couple helpful links if you want to look more into the Slurm scheduler. Again, Complex provides, I think, an entire hour session on schedulers. Specifically, if you want to know more about the CEF and S-ACIT command, and then the basic training catalog. So thank you very much. I'm going to stop sharing so that I can see the chat and open it up for any questions.